Inside a modern desktop processor, the arithmetic logic unit executes complex mathematical operations in a fraction of a nanosecond. But that speed is entirely useless if the processor has to wait for data to arrive. If the pipeline runs dry, the entire system stalls, wasting billions of potential calculation cycles. To prevent these stalls, a computer needs data readily available. Yet no single physical material exists that can maximize data density and bandwidth while simultaneously minimizing latency and fabrication costs. This chart maps the 5 critical vectors of memory performance: capacity, latency, bandwidth, volatility, and cost. A hard drive might push the capacity and cost axes to their absolute limits, but it fails on latency and bandwidth. Conversely, the processor's internal memory pins the latency axis, but shrinks capacity down to mere megabytes. Because no single medium achieves a perfect score across all 5 vectors, hardware engineers orchestrate a precise spatial and structural hierarchy. By layering different physical materials and storage techniques at varying distances from the processor core, they create the illusion of an infinite, instantaneous data supply. To see exactly how this illusion is maintained, we will trace the path of a single digital bit, starting at the processor's execution core and moving radially outward through the entire hardware stack. When you read the spec sheet for a new computer, the listed access times, whether measured in milliseconds or nanoseconds, are not arbitrary software limits. They are the deterministic results of nanoscopic circuit layouts and physical signal propagation delays. Understanding the true speed limits of computing requires stripping away abstract metaphors like cloud storage or digital libraries and directly examining the physics required to trap and measure an electrical charge. We begin at the innermost layer of the hierarchy, the CPU registers. Sitting directly adjacent to the arithmetic logic unit, registers are built using D flip-flop logic gates. Because they are woven right into the execution pipeline, registers can feed data to the logic cores in a single clock cycle. That is an access time of roughly 1/3 of a nanosecond. This schematic shows a static random access memory, or SRAM cell, which makes up the L1, L2, and L3 caches. Storing a single bit of data here requires 6 individual transistors, configured to hold an electrical signal in a continuous interlocking loop. 6 transistors per bit is an enormous structural cost. When we multiply those 6 components by the 36 megabytes of storage required for a typical L3 cache, we get an array containing roughly 1.8 billion transistors. At that scale, cache memory consumes approximately 1/3 of the processor's entire physical die area. Expanding the cache any further would require enlarging the highly expensive silicon die, pushing manufacturing costs beyond commercial viability. Operating at single nanosecond speeds necessitates complex, continuous power circuitry. Because this architecture consumes so much physical space, the top tier of the memory hierarchy is permanently constrained to a capacity of mere megabytes. Moving outward from the processor package, the data path travels across the physical copper traces of the motherboard, reaching the main memory channels. This diagram compares the 6-transistor cache cell against the architecture of dynamic random access memory, or DRAM. DRAM utilizes a 1T1C architecture, pairing exactly 1 transistor with 1 microscopic capacitor to represent a single bit. Instead of an active electrical loop, data is stored passively. The capacitor accumulates and holds an electrical charge, functioning as a tiny physical reservoir. A filled reservoir represents a binary 1, and an empty one represents a 0. Reading this data incurs a latency penalty. The processor routes a tracking signal through specialized sense amplifiers, measuring the precise electrical charge held inside the capacitor. Combined with the spatial distance traveled across the motherboard, this retrieval process takes roughly 45 nanoseconds. Furthermore, capacitors are inherently leaky. The stored electrical charge constantly dissipates into the surrounding silicon. To prevent total data evaporation, the memory controller must actively rewrite, or refresh, every single capacitor's charge multiple times per second. By sacrificing electrical permanence and accepting the latency of traversing the motherboard, engineers compress gigabytes of data into a small form factor, driving down the physical cost of capacity. The data path finally exits the volatile memory layers and terminates at the permanent storage drives, specifically the NVMe solid-state drive. This array represents the core structure of 3D NAND flash. Memory cells are arranged in a dense grid and stacked hundreds of layers tall to maximize density within a single silicon die. Inside each cell is a charge trap structure. By applying specific voltages, electrons are forced into an insulating dielectric layer where they become permanently suspended. Because they are physically trapped inside the insulator, the data remains intact for years without drawing any external power. However, lacking a direct electrical loop or simple capacitor connection, measuring these trapped electrons requires applying a complex, carefully timed sequence of voltage steps. While vertical stacking unlocks terabytes of capacity at a low cost per gigabyte, the physics of interacting with the dielectric insulator pushes the baseline access time out to roughly 80 microseconds. Even slower is the mechanical hard disk drive. Its massive capacity and microscopic cost per bit rely entirely on a physical read-write head scanning across a spinning magnetic platter, constraining access times to the 8.3 millisecond rotational limits of the motor. Achieving true non-volatile state permanence forces the abandonment of instantaneous electrical logic loops. The resulting reliance on physical trapping mechanisms creates a massive latency gap between main memory and permanent storage. While the standard desktop hierarchy effectively balances general tasks, modern AI accelerators and large language models introduce a workload profile with significantly higher data requirements. This diagram illustrates how an AI comprehends a single word token. It doesn't process text, it processes geometry. One token is mapped to an array of roughly 8,000 distinct values, or dimensions, establishing its attributes and relationships. When feeding a state-of-the-art model a context window of 1 million tokens, the math is direct. 1 million tokens multiplied by 8,000 dimensions requires keeping 8 gigabytes of active data loaded at all times. To generate a single response, that 8 gigabyte data block must be continuously fed back and forth through hundreds of billions of transformer parameters housed inside the processor's core. Traditional planar motherboards cannot handle this bandwidth. Funneling gigabytes of active data across physical circuit board traces to standard memory modules introduces a spatial distance latency that becomes mathematically catastrophic to the accelerator's processing time. The spatial separation that made the desktop memory hierarchy functional actively works against AI. The processors are effectively starving, waiting for data to travel across the circuit board. The solution to this crisis is high bandwidth memory, or HBM3E. This architecture removes main memory from the planar motherboard and relocates it directly onto the processor package itself. By placing the memory directly adjacent to the AI logic cores, engineers eliminate the transit time across the motherboard. This cross-section shows the engineering breakthrough that makes high bandwidth density possible through silicon vias, or TSVs. Instead of laying memory chips side by side, up to 12 memory dies are stacked vertically, with conductive columns drilled straight through the solid silicon layers. These TSVs function as microscopic vertical highways. They link the individual layers together internally, allowing signals to route straight down the stack without relying on external wiring or pins at the edge of the chip. The electrical signals travel down these columns and feed directly into a dense silicon interposer, which serves as a highly conductive bridge routing straight into the AI processor core. This exact physical proximity and parallel vertical routing delivers 1.2 terabytes per second of bandwidth with profoundly minimized spatial latency. While the immediate processing occurs on this tightly bound chip, the broader AI data center architecture still demands extreme scale. Petabytes of raw training datasets are relegated outward to networked data lakes using massive NVMe storage drives to support the long-term pipeline. Scaling compute performance now relies on engineering tighter, 3D integrated physical hierarchies to feed continuously data-hungry processors.